Hello, everyone. Happy holidays. Be well, be safe. This podcast, Ep13, is packed full of information. Yes, throughout the 2 hours, there are bits and pieces where there are more information, but it is all the way through the entire podcast, all 2 hours. For those who are not familiar, we created AsteronX and Iris in order to create an interstellar project. Enjoy the podcast.
What constitutes a jump drive? How do we define a jump drive anyway, versus other forms of propulsion? What makes a jump drive a jump drive? A jump drive is a discontinuous drive, a teleport drive, so to speak. A starship equipped with a jump drive effectively tunnels through space-time. In one instant, the ship exists in location A, and the next it exists at locations A and B at the same time, and in the third, the ship is at location B only, having moved across a vast distance instantaneously, and existing nowhere in between. Is a warp drive a jump drive? Not all warp drives are jump drives, no. It may be possible to travel fast in light without an instantaneous jump. Therefore, that's not a jump drive.
Well, I know right away everyone's going to ask, what about a wormhole? Is that a jump drive? Is that a warp drive? I know they're going to want to ask.
Okay, that depends. Let's see, it's not a warp drive, first of all.
Right.
There's similarities, they both warp space, but a warp drive creates a space-time bubble, whereas a wormhole creates a space-time tunnel. You can kind of think of a warp drive like a wormhole that's closed at both ends and only opened at the destination.
A warp drive, yes.
Yeah, you can kind of think of it like that. And how close of an analogy it is depends on how separated, detached from space-time that a warp drive is. But is it a jump drive? If the wormhole is naturally occurring somehow or created by a stationary machine, that's not a jump drive, but that could be called a jump gate.
I think...
But if a ship... Hold on.
Yeah, go ahead.
If a ship goes ahead and creates a wormhole on the fly as it needs it, then I'd call that... It can be a jump drive with a caveat.
Yeah.
Every wormhole has a throat. That's a space-time that connects one part of it to another. Mm-hmm. You're probably familiar with the diagram where it shows what looks like a drain pipe going down and then back up.
Yes. Yeah.
You have to keep in mind that that's an incomplete analogy. It's
very simple, very basic.
Kyle Haley recently did a video about looking for alternative explanations of wormhole other than the tired old pencil through paper analogy.
Yeah.
It's a tricky thing because if you fold up some piece of cloth or paper and make a hole through and say wormhole, or anything else like that, the problem is that that's not really what's happening because space isn't being folded up to make space smaller. It's that the wormhole is going through a different medium where distances are compressed. So the space outside the wormhole is the same as it always has been, yet at the same time space is shorter through a wormhole. Actually, you know what a better analogy is? Because I suppose technically, if all of space-time were completely flat, wormholes could not work. They would be no shorter. Mm-hmm. They can work because hyperspace as a whole. Then hyperspace, by the way, isn't just a thing in sci-fi. It's a scientific term that refers to more than 3 dimensions. That means there's a hyperspace of the past, of the present, of the future. Well, actually multiple of the past, multiple of the future. Every combination of more than 3 dimensions is a hyperspace. Mm-hmm. Every instant in time is a hyperspace. Mm-hmm. And of course, with a parallel negative space-time, that plus normal space-time is a hyperspace.
Yeah.
So, because the universe, as the material physical universe, is embedded in this hyperspace, it's not flat. It's curved in that. In fact, there's that one paper that came out not too long ago where they did a exhaustive study from many different sources, cosmic microwave background, distant stars, etc., and came to the conclusion that the most probable shape of the universe is basically a 4-dimensional or higher dimensional version of a torus.
Yes.
It's not like a torus is a circle that's then moved in a circle that is then, you take a circle, you define some point to the side of the circle and make sure the circle is at right angles to that central point. You then take the circle and move it. Let's see. You don't move it parallel with any of the lines that make up the circle, but perpendicular to them all. Whereas you take a circle and move it around another circle, so that always remains the direction moving in is always perpendicular to the circle. So you also rotate the circle. Yeah. And that describes that a torus. You can do the same thing, but say with a sphere, and you move it through 4 dimensions, and that creates a torus made of spheres. It's, higher dimensional nonsense.
Yes.
Because the universe as a whole is curved, that's how wormhole can work. The analogy is Earth is a sphere. Its surface is curved. But so is a gravitational field that pulls us down. And so therefore gravity is always perpendicular to the surface. But if you go and dig a tunnel, say cutting straight through part of the Earth, it's a shorter distance through that tunnel than it is going over the curved surface. That's probably the best analogy for a wormhole. And in that sense, if you can take a wormhole and make the throat inside arbitrarily short, like infinitesimally short, so it has practically no length, then even though the two sides of wormholes the wormhole is very far away, if a ship or machine goes and creates a wormhole that has a distance through it of basically 0, then that's a jump system. If it's a ship and it's moving, it creates on the fly, then it's a jump drive. And you could shorten the throat, or alternatively, if the throat had a non-zero length, but you went through it so fast that time dilation meant that you going through it experienced no time, that would also be a jump drive, because the wormhole's ends can be adjusted in space and time, theoretically, that the two mouths of the wormholes exist at the same time. Like, in other words, if you were to travel with at no time between them, you'd find that they're at the same spot, or same place and time, so to speak. As much as that makes sense with relativity. And in that sense, that would be a jump drive also. So, a wormhole is not all wormholes are jump drives. They're not warp drives, so there's some similarities. And some wormholes can be jump drives. To finally answer the question.
Yes. I'd like to add one thing in here real fast before we get too far away from the beginning. Also, you guys, we will make mention to what Dr. Harold Whitehead recently, from former NASA employee, had recently discovered. We'll talk about that a little bit. Before we get a little deeper into this, it seems that some are not aware Renee and I are co-founders of AsteronX and IRIS. So we do this
for International Research Institute for Space.
Exactly. We do this work together. Renee, tell us, is this ship going to experience any time while it's in a wormhole? Any travel time?
Well, I did sort of just go over that. It depends. It it depends on two things. How long the wormhole's throat is, and how fast the ship is moving through it.
Okay.
So, or alternatively, you could create a kind of inverse warp bubble around your ship and create time dilation even at slow speeds.
Well, there's another question too, is when the ship enters the wormhole.
One question at a time here.
Yeah.
Yeah, so it depends on the length of the throat and the time dilation experienced. So if the throat is basically if the throat basically has no length, if it has a length of 0, then there's no transit time. In which case, going through it would be kind of feel like going through. Well, it depends. If you had like a gate that produced a wormhole where the mouth was actually flat, in 3D spacetime, that is.
Yeah.
Then it would just seem like going through a gate or a window. You just have a machine in space and you fly through it. You look through it first of all, and you can see the other side.
Yeah.
And if it's far enough away that the constellations are noticeably different, you'd look through and see a different star pattern through it than around.
So,
and as you fly through, it would be just like you're going through a doorway.
A doorway, yeah. Or a stargate, something like that.
You might have a bit of a Cherenkov glow around any objects on the edges of the field of the throat as you go through. Maybe. That hasn't really been studied much because relative to where you were, it's as if bits of you are going fast in light, so...
Well, there's a...
Only relative, so in other words, there might be some complaints from space-time resulting in some harmless blue Cherenkov radiation.
Well, that raises, of course, actually, I was going to ask a question, but I wanted to save this. What do you think of the analogy that the wormhole is in effect a higher dimension where the speed is much higher than the speed of light that connects 2 points where the speed of light is slower?
No, that's an incomplete analogy.
Yeah.
For one, yes, like I just said a little earlier.
Yes.
We exist in a hyperspace that's anything more than 3 dimensions. And beyond the physical space-time, the limits on the speed of light are different or non-existent. It's not so much... It's an incorrect... To imagine that hyperspace is some different space-time where the speed of light's higher is incorrect. Hyperspace just means... It's just like saying the word hypercube. It's just simply refers to a higher dimensional space-time, like it has more than 3 dimensions.
Yes. More than
Which means right now we are living through and talking through every time an instant passes, there's another hyperspace we've passed through.
Right.
The past is made of a whole pile of hyperspaces, and as is the future. So... and then there's the negative space-time. No, the negative space-time is closer to what people imagine when they think of hyperspace. So that can also be called superspace.
Yes.
So in superspace, superspace is made of what's called time-like dimensions. That means that you have to actually go fast in light to move in them at all.
Right.
And therefore, relative to us, it appears to be filled with nothing but tachyons. Flip the perspective around, instead it appears to be normal, and we're made of tachyons. Yeah. Although there's some caveats there, but that's another topic.
Yeah.
It's not quite symmetrical in that regard. Well, basically, or like this, it's if you have 2 tachyons going opposite directions, to give an extreme example, if you switch to the perspective of one of those tachyons, that tachyon now appears to be stationary to itself, like everything.
Right.
And it's no longer a tachyon. But the other particle that was a tachyon to a particle that moved slower than light is still a tachyon to this tachyon.
Yeah.
So therefore, in super space where everything's moving tachyonically, any given tachyon will still see a lot of, even most of the other tachyons still as tachyons. So it's not a perfect symmetry, mirror symmetry, where you can just simply flip the perspective and it all looks normal.
Right.
But that's a topic for yet another video.
Which is coming.
Yeah, and by the way, the singularity video is still underway, but it's long, and we want to make sure it's done right. So expect it sometime in the next, I'm gonna say probably January. I hope not February, but probably sometime in January.
Yeah, we have a lot of work. There's a lot of things we're doing. The time is...
It's basically a documentary. It's a full-length documentary.
Yeah, and I'm also letting them know about, just as the video I'm working on, the reality of achieving faster than light interstellar travel. You know, it's a long video. Looks like it might be 2 hours. I'm going to try to shave that down. I think that's too long. But we have a lot of things to do. And we also want to start maintaining at least one podcast per week for our channel. It's important.
On either, generally we're aiming for Thursday or Friday, sometimes Saturday, but generally at least once a week, sometime in the second half of every week.
There was a time when we thought that, wow, we're going to get all these topics out. We're going to make all these videos. Time just passes, as everyone knows. Time flies.
That said, I'm also simultaneously working on a shorter video to come out sometime in the next couple weeks.
Yeah.
About jump drives. So this podcast you can think of as a bit of a precursor.
Yeah. And I'm also working on...
I'll put it this way. If you guys, if enough of you guys watch this podcast, then it will be an encouragement to hurry up with the full video on the jump drives.
Yes, it will be. Yes.
Hint, hint.
Hint, hint. And as I was about to say, I'm also working on a shorter video, maybe around 11-15 minute range. I'm going to talk about realistic near term, what we could practically build today. So, but as I was saying a moment ago, when we first started, we wanted to create a whole bunch of different videos about a whole bunch of different topics, all pertaining to interstellar mission, which we're striving for. But the time has gone by. The best way for us right now, before we can get the videos out, is to share this content through these podcasts. So if you look at our channel right now, we're starting to get more of a variety of related topics.
I want to say something on this in a minute. And
yeah, go
I just
ahead.
want to make this brief because this should be a podcast and a dedicated video on its own.
Yeah.
I'm going to summarize it like this.
Mm-hmm.
We created AsteronX. We didn't know it at first, but we eventually came to this conclusion, and this is what we have been working on for the past 2-3 years now. Our mission is to establish a settlement on a habitable exoplanet before this century is over. Yes. We're drawing up a plan. We have a rough plan right now involving creating a sort of interstellar fund that can fund any and all projects that are working toward this. We're also intensively researching the necessary technologies to make this happen.
Mm-hmm. That's right.
I don't want to go into much detail right now because it takes us too far off the main topic of the video, but we can come back to this.
Yes.
We are already in contact with several different people in the interstellar community, including Adam Crowell of Acars Interstellar.
Mm-hmm.
We're slowly trying to pull together and create something of a team, not just to do another design concept, but to say, all right, we want to, before the century's over, establish a settlement on a habitable exoplanet in another source, a habitable exoplanet, and we want to do it before the century's over. So we need to, if that means having to push the boundaries and develop new physics, then that's what needs to be done.
It's doable.
And yeah. And if you've watched our videos, you'll realize that manipulating space-time not as hard as it seems. Like,
yeah.
Here's a small example. The million Tesla magnetic field produced by a neutron star is enough already to polarize the quantum vacuum. Light that passes by a neutron star becomes polarized from the magnetic field.
Mm-hmm. That's right.
And the thing is that those are simple magnetic fields. And what's been a little bit overlooked is that we've had these more complicated theories to do with the weak and strong forces derived from Maxwell's equations for the better part of a century now, or more than that. I'm not sure exactly how long, but we've had them for quite a while. But it's not looked into often, going and combining those with ordinary EM equations, seeing,
right,
well, is that all there is to electromagnetism? Is there really nothing more to learn about it? It's kind of analogous to when chaos theory is born. They realized that what they thought was a done and dusted field, hydrodynamics, they were just barely scratching the surface. In hindsight, we can look back and say, wow, we had really no understanding of hydrodynamics back then, and they thought they were nearly done with it.
Yeah, it opened
likewise,
whole new
electromagnet. There are what you can say higher order electromagnetic fields, more complex electromagnetic fields.
Yep.
One relatively simple one is where you cancel the field out. It doesn't just go away. You can never destroy energy can't be created, destroyed, only transformed. Mm-hmm. So ask yourself this: when a magnetic field is neutralized, where does that go? Normally, we just say, oh, well, there's this vector potential, but that's non-physical. That's not a physical field. Well, it turns out if you add in and this actually is tangentially related to the jump drives in terms of how to achieve it.
I was just thinking that.
Yeah, it turns out if you add in what's called gauge symmetries, the more complex, newer theories to electromagnetism, it shows that there's something being hiding under our nose. What we thought was just a magnetic field neutralizing itself with this non-physical, non-real, just on paper vector potential, actually is a very real field, a tensor field, in fact, more like gravitation.
Yes.
Now, I don't want to go any further on that because that requires a whole nother lengthy explanation, but basically, there are higher order EM fields that couple to space-time more strongly. Because it's not that gravity's weak. To paraphrase Frank Wilczek, I'm paraphrasing because I don't remember his exact quote, but to paraphrase Frank Wilczek in his book, it's not that gravity's weak. It's that the question isn't why is gravity so weak. It's that why is matter so lightweight? Like, why does matter, or rather, to put it another way, to think out more like a physicist does, why does matter couple to space-time so weakly? And that is the right question.
Yeah,
that's the correct question.
That's right.
And it's these higher order, these more EM fields, these more complex EM fields, actually couple to space-time more strongly than ordinary EM fields do. And therefore, in a sense, you could say they don't follow the normal E equals mc squared. That's kind of sort of the coupling of EM. And you can also say that the missing mass is actually drawn from the quantum vacuum. Hence, these more complex EM fields are a way to actually build a quantum ramjet.
Yeah, now you're leading into another territory there.
Yep, that's why I wanted to.
But I just wanted to make sure. That's why I'm trying to ask questions that I think others, also trying to remember all the myriad of questions people have asked. But I just wanted to make clear that what you were talking about is when you take two magnetic fields that are canceled.
Yeah, you make them oppose each other.
You make them an equal and opposite. And they will cancel, and what is left, what's the result, is this field that Renee is talking about.
Mm-hmm.
So it's real. Okay, so getting back to when entering a wormhole, do you still require a warp bubble? And I know somebody asked that question once before.
No. You don't need a warp bubble at all, because
it's one or the other.
If you had the right... In fact, there's some work by Leonard Susskind and... Oh, what's this? There's another scientist. I don't remember his name. Are
you searching it?
Yeah.
Okay.
Okay. Leonard Susskind and one Maldacena.
Okay.
What they showed is that a wormhole is actually equivalent to entanglement.
Yes.
In other words,
yes, that's right.
Entanglement may actually be wormholes connecting bits of matter, not big enough for the matter to get through, but enough for some information to convey in some manner.
Which means that it, obviously, as we know, entanglement is instantaneous.
So, now, if you could take a naturally existing wormhole, like maybe entanglement, an entangled particle, the renowned physicist Kip Thorne, he showed how if you actually had a sphere where if you could make a wormhole and you had the two ends and you put around each end a sphere where the gap was extremely small, because the wormhole has a near zero length through it in that particular case, the plates, even though they're the two spheres, even though they're technically far apart, are effectively inside each other through the wormhole. So that means that the distance is very small, and that means Casimir effect, negative energy. Which brings us to what White did.
Yes.
And with that sphere technique, you could take a wormhole and stabilize it, hold it open. And then you just make a hole in the sphere somewhere, and you can fly through. So what White did, as this one article put it, no, he didn't create a warp drive, but he has made another step that, in a way, is not surprising, but on the other hand is also an important confirmation of this whole field.
Of the field of warp drive and jump drive.
Warp drive mechanics.
Yes.
So, what he found is that, so he took two plates, put them really close together, and then put a cylinder inside and then a sphere inside that cylinder. And he measured what was happening to the quantum vacuum, the background energy fields that fill all space-time. He measured what was happening to it. The distortion was happening around the little silicon bead he had in there. Silicon sphere. And it was distorting, and in fact distorting in such a way that it was becoming negative, or was negative. So in other words, the quantum vacuum around the sphere had become negative in energy.
Yes.
Not effective negative energy, but true negative energy. Which, of course, has many other physicists tearing their hair out. But like I've repeated so many times, and I will keep repeating ad nauseum, tachyons are not a problem. They do not break physics. In fact, if you add tachyons, the once mysterious behavior of the very small quantum mechanics, where we can't really make sense of what's actually going on with it, makes sense. Like that paper, the quantum principle of relativity. I'm going to keep repeating about this paper because more people need to know about it.
Yes.
What's her name? Eckert and Dragon, that's their last names, I remember them. They were in this paper, and they showed how if the particle is, some part of it is capable of superluminal, then it doesn't break causality. In fact, instead, what happens is the particle exhibits indeterminacy, quantum indeterminacy. It makes sense if you think about it, because tachyons, they go faster the less energy they have and spread out, so it's like a wave. And they can do things like exist in multiple places at the same time. And because of that, if there's emanating from a particle, if the particle's sort of awesome between tachyon normal, then it can create a fuzziness to the particle, where because it's half the time made of tachyons, you can't exactly pin down its location because it's technically existing as a tachyon cloud in multiple spots.
Yes.
Just sort of concentrated more in the center.
Yes, exactly.
And so and that's purely in relativity. In that paper, the quantum principle of relativity does not actually use any equations of quantum mechanics and just is based on relativity, which means, yes, it is a unification. So that touches on our own addition to that field that we're working on right now with a equation that describes a time quantum.
Yes, right.
Just like a photon is a quantum of electromagnetism, we've found an equation that describes a quantum of time.
Now,
so
White's experiment does to some extent start to prove the existence of negative energy. So,
well, it does prove it, and it starts. Yeah. It's another notch of confirmation of the likely existence of tachyons.
Yes,
there is an experiment proposed by Dr. Takaaki Musha, being the Musha jump drive that we referenced a long time ago now.
Yes.
And he proposed an experiment where you could get a photon or electron or some other particle to accelerate and tunnel through space-time effectively. Which I'm going to come back to that whole idea because that's what this podcast is about.
Yep.
If that experiment were carried out and was a success, what would it mean? What it would mean is that you'd have a particle like a photon or electron. One moment it's across the room. Next moment it's traveled 3 meters and is on the other side of the room. Instantaneously. And because of it, the nature of it, information, it could carry information fast and light.
Yeah.
Which on that, I want to say one more thing.
Yeah.
There's a paper that actually talked about this.
Mm-hmm.
Just because we have tachyons and causality maybe under certain circumstances is not strictly cause and effect, is not always strictly true. But it doesn't break all of physics because guess what? Everything we've already know about and measured and detected and experimented with can still be described by conventional physics and conventional cause and effect.
That's right.
Yes, it means that future experiments and research is carried out with tachyons and maybe even with quarks in some circumstances may have to take a different approach and can't make the assumption of cause and effect always being held true.
Right.
Probably meaning you have to instead take an approach where you deal with things in a atemporal and a timeless state, and you describe more like what the overall shape of it in hyperspace looks like.
Yeah.
And then you can take different snapshots and slices through that to show what it would look like from different points of view. Which has kind of been what relativity has been all about from all along, but we need to embrace that more. So a lot of the assumptions in particle physics are going to have to be abandoned going further. But that does not mean that it invalidates everything we've already done. That math still works and makes valuable predictions.
That's a great point. Yeah.
Using the pre-existing equation that can simulate a proton and tell you if you do in this or that to a proton, that the quarks are disturbed in this way and this happens. It doesn't actually kill all of physics.
It doesn't break physics. That's right.
No.
It adds to it, but doesn't break it.
This is something I very much hope does not happen, and that is,
yeah.
I do hope that scientists don't start running around like headless chickens when, especially particle physicists, when tachyons are, and because Todd and I we're at this point, given the research we've done, are convinced that yes, tachyons are very much real.
Yeah.
And not just, I want to make it clear, it's not that we believe they're real, it's that there's enough evidence accumulated that we are convinced that they are more likely to be real than not.
It just makes sense. The universe...
It's the logical conclusion from the evidence before us.
The logical conclusion.
So one thing that I really hope does not happen, is why I'm saying what I'm saying right now, is what cannot happen is a bunch of scientists running around saying that we discovered tachyons, it means all of physics is void. That's an overreaction and not actually an accurate statement. It does not invalidate everything.
It's an irrational reaction. And yet, we're probably going to see some of that anyway.
Well, I hope the more we say things like what we are right now, the better. And you guys listening, repeat these statements to as many people as you can. Tell them about how tachyons don't break physics. In fact, they solve some long-standing mysteries, and existing physics still works for the known particles.
It explains the more of the universe than we've ever experienced before.
Now, so back to wormholes then.
And jump drives, yes.
Yeah. Actually, I think we've already talked about.
I think we've covered the wormhole pretty good.
Yeah.
I'm eager to get on with jump drive.
Okay, so the first thing I want to say about that, actually.
Okay.
And then you can see something?
Yeah.
So, jump drive, in fact, any FTL kind of works like this. Imagine you had a ship that traveled in an extremely high fraction of the speed of light. Let's say it traveled 3,000 light years. And then when it got there, jumped back in time, using tachyons, let's say, 3,000 years.
Yes.
Ignoring where it's going in between, because of the extreme time dilation, the crew and the ship only felt like a few fractions of a second. Like, let's say it was that extreme of a time dilation.
Mm-hmm.
And because it jumped back in time to any people at the destination or the departure point, it was instantaneous. Now imagine that you then were, as you were traveling, jumping back in time always. So in other words, you travel for one second at practically the speed of light, and you're jumping back in time 1 second. Like, you're always reversing your time.
Mm-hmm.
It's not so much that you're putting a big reverse button on the whole universe. It's that you are jumping your ship back in time constantly.
Mm-hmm.
So you travel, jump back in time, travel, jump back in time, and
you're
doing it repeatedly.
Yeah.
Yeah, or not continuously, but kind of
continual.
Like, hold on, not continuously, but continually.
Yes.
In other words,
that's right.
Continuously is where it's without pause. Continual is where it's ongoing, but with intermissions.
The correct word explains it better. Yes.
Yeah. So it's continually jumping back in time as frequently as it can.
Yeah.
Let's say that's, if possible, once every time quantum, which we can call a chronon.
Okay. Yep.
So every quantum of time, it jumps back in time, one time quantum. What that will mean is that if something is traveling through space but exists, let's see, I'm referencing my notes here. So if a thing exists somewhere for 0 time, then it doesn't actually exist there at all.
Right.
There's no time to interact with anything. There's no time to be visible, to run into anything, or any interaction whatsoever.
Mm-hmm.
So if a ship travels through space, but constantly is jumping back in time equal to however far it's traveled, then it exists for no time.
Nowhere.
In that in between.
Nowhere. Yeah.
The only places that it exists for any length of time is just before it engages its drive and after it's arrived at the destination. Which means effectively what's happened, and if the crew are experiencing extreme time dilation, so they don't experience any time, then to all parties involved, the ship, as far as everyone's concerned, has just instantaneously jumped 3,000 light years. And that's basically the working principle behind the jump drive, and also is a bit of an explainer about why FTL travel is equivalent to time travel, why they're the same.
Yes, right.
Basically, any FTL travel is where you are going back in time equivalent to all or large fraction of however long you've traveled for. Like if you travel for 1 light year at just under the speed of light, and then jump back in time, say 5 months, then you've gone fast and light as far as everyone's concerned, because you can, and more sophisticated, you can view it like this, that a ship, rather than just traveling 1 light year over the course of 5 months, if you say, or over the course of a year, if you say that it's traveled 1 light year over the course of 5 negative months plus its travel time, basically it's traveling backward in time as it's moving forward through space rather than moving forward through time. Or rather, the drive is trying to make it do that, and that's mixing with its pre-existing forward time motion to partially cancel it and leave it going through time faster than going through space faster than normal.
So explain to him, why does it go back in time when you're going FTL?
No, there isn't a why. It's that any FTL motion must also be backward in time motion, for like I just explained. If you travel for a year at just under the speed of light and then jump back in time 5 months, then you've traveled at twice the effective speed of light.
Mm-hmm.
So normally, if you imagine a diagram where time is vertical, space is horizontal, the speed of light is a 45-degree line.
Mm-hmm.
And as you approach that, you slow down. Or it's not exactly true. That needs more explanation, but
give him
a good enough.
Yeah, just give him enough.
Get a close enough analogy for the purposes of this.
Yes, exactly.
So, if you travel just under the speed of light, like nearly a 45-degree line,
mm-hmm.
But if instead you have a drive that's trying to push you backward in time,
yes.
So a drive that somehow sets up a reverse time field, but you're already moving, the two counteract each other.
Mm-hmm.
So that you instead end up, let's say it negates half of it, tries to make your time, rather than going forward at time at the normal rate, if you were standing still, you might go backward in time at half the speed you're currently going forward in time.
Yes.
So that you'd be experiencing reverse time, but everything would take twice as long in reverse. If you then are going at high speed, just the speed of light, and you combine the two, then effectively the two are counteracting, so you end up instead, rather than going at 45, you end up at a 67.5 degrees.
Yeah.
And you're now traveling through time faster than light can. And
yes.
The only way to do that is to go backward in time.
Yes, so just so they have an idea, the graph, the 45 is the speed of light. Anything higher or lower is slower or faster than the speed of light.
Anything that's, so in other words, 45 to... So if if we put 0 degrees as straight up,
mm-hmm.
40 positive or negative 45 degrees is the speed of light in either direction in space,
mm-hmm.
which is on the horizontal axis.
Yes.
Anything greater than 45 plus or minus 45 degrees from the center line
mm-hmm.
is FTL speeds, and anything less than 45 is slower than light.
Right.
Anything greater than 90 is still FTL and is now actively going backward in time.
Yes.
Which means that it will arrive at its destination before it even leaves.
Yeah, you could...
But here's the thing.
Yeah.
If you go fast in light,
mm-hmm.
from the point of view of like where you leave and from and where you arrive to,
mm-hmm.
you are going straight horizontal, like you travel that distance in 0 time. From certain other points of view of vehicles moving at high speed, they'll actually see you arrive before you even leave.
Mm-hmm.
That is the wacky true nature of fast and light travel.
Yeah. Yeah, because as I've stated before, and I think I need to state it again, the rate of time that passes that we observe is fixed at thereabout the speed of light, which is variable to some degree.
So to put it another way,
Yeah. Please.
That means that any change in anything only propagates out at the speed of light.
Right.
So hence time can be said to move at the speed of light, because any change can only affect other things at the speed of light.
Like an apple decaying. Yes.
Therefore, by definition, anything that moves faster than light is moving faster than changes can propagate.
Yes.
Hence it's moving faster than time.
And hence my not accurate description to say the speed of time, which doesn't have a speed, just to let everybody know.
Basically, the speed of light just happens to move at the maximum speed of change of anything with positive energy and normal mass and positive energy.
So the speed of light is the fastest rate at which things can change from luminal down to zero, to rest.
And by the way,
Mm-hmm.
I can give a little explainer here about what's up with tachyons. Why do tachyons have what's this with nonsense with imaginary mass?
Yeah, and just to let everybody know before you do, again, this is all related, you guys, to jump drive. So, okay, please carry on.
Okay, so I'm referencing actually a script that's in progress for a tachyon mechanics video that will come out after the singularity video.
Mm-hmm.
Nice. Let's see where's my reference.
Nice, very nice.
So, first I want to explain, for those of you who aren't familiar with it, what an imaginary number is. Okay, so it goes like this. You multiply a positive number by another positive number, and you get another positive number. Simple enough. But multiply a negative number by another negative number, and you also get a positive number. You can try it. Open up your calculator and say go -3 times -3, and you get positive 9. So it poses a conundrum. What's then the square root of a negative number? So take -9. So you square that, you go -9 times -9, or you on the calculator go -9, put a little caret, and put 2. That's a square. Oh, sorry, sorry. So, okay, you take -9. Positive 9 has the square root of 3, because 3 times 3, so 3 squared is 9. So the reverse of that, the square root of 9 is 3. But what about -9? You might say that, well, okay, maybe -3 should be the square root. But try that. -3 times -3 is positive 9. Because two negatives times each other is positive.
Yes.
In fact, it's worse than this. In fact, you cannot find a number that when multiply itself equals -9 or any other negative number. So mathematicians invented, or depending on your point of view, discovered
Yeah.
a new kind of number, which they called imaginary number. And so they basically defined it. And if you say, like, oh, that seems like cheating, that's how all of mathematics has come about, is that they couldn't solve something, so they created a new approach to it, and now are routinely using it.
It's a tool by which to figure out these things.
Imaginary numbers are used routinely in calculating rotation, in both in the outside world with real world with radar and whatnot, and also even games or simulations to calculate rotation. If we didn't have imaginary numbers, you could not as accurately track airplanes coming into an airport, airliners,
or GPS. Yeah.
What instead you do is, if you have, it's defined like this. Imaginary numbers work like this. You type 3i, so you can try that on your calculator. I for imaginary, which is a bit of an unfortunate name because it's not really imaginary, but that was how it was looked at the time. So 3i times itself equals -9. That's how it's defined. Depending on your calculator, like mine right now is moaning at me, but depending on your calculator, you might be able to do this equation. But 3i times itself is -9. 5i times itself is -25, and so on. Basically, think of imaginary numbers like this. Ignore the little I and treat it like you would an ordinary positive number. Let's say you have 7i. Start by taking the square of plain old 7. So that would be 49. Then make it negative. And there you go, and that's the square of 7i. So, what was found is that due to the way the equations of relativity work, if you have a particle that's moving faster than light, you find that its rest mass, so its baseline mass, the mass that it would have if you could somehow bring it to a standstill, which for tachyon you never can, because the speed of light for a tachyon is a lower limit.
Yeah.
But if you could, in theory, make it stop moving, its rest mass would be an imaginary number. So, what exactly does that mean? You can kind of show it with a little equation. It's the equation for the velocity-energy ratio. And we can put it on screen. It reads out like this. E equals mc squared over the square root of 1 minus the velocity squared over the speed of light squared. Now what happens, and I won't try to go through right now, but basically what happens is if you run through the equation, you find that if you put the velocity as anything greater than the speed of light, and it doesn't matter if you put the speed of light, type it out in meters per second, or you just say speed of light equals 1, like 1 times the speed of light, and you put 2 times the speed of light on the top part, it doesn't matter. If the velocity is over the speed of light, the equation spits out a imaginary number as the energy of the particle. If it's the energy is an imaginary equal to an imaginary mass. So whatever the mass is, you take that and multiply by an imaginary number, and that's your energy. Now, when they discovered that, many just said, "Oh, well, I guess they're not really physically meaningful then." But one scientist, Dr. Froning, saw something else. After long days of thought, he came up with a solution. The imaginary mass meant that a tachyon did not move within our dimensions. It's like this. Just as there's a number line from -infinity to +infinity with 0 in the middle, there's another number line going from -infinity I to +infinity I, with 0 again lying in the middle. In other words, imaginary numbers create an additional dimension in number space.
Yes.
Which, it's extended, by the way, by quaternions, which add two additional imaginary numbers j and k, creating a number space of 4 dimensions, which can be used to elegantly describe relativity.
Yeah.
It's actually simpler that way. But that's another topic.
Yeah.
So, similarly, Froning pictured a parallel superspace, a negative space-time, as we now know is practically mandatory.
Yes.
So he pictured a parallel superspace with 3 dimensions, each marked by an imaginary number, in which tachyons can move freely, similar to the number space dimensions created by imaginary numbers. So the imaginary rest mass simply meant that tachyons could not be at rest in our space-time, but they could be in superspace. So in other words, it's saying that the I was a marker indicating superspace. The tachyons possess this rest mass, but only in superspace. Does that make so? Do you have any questions? It's maybe if you can ask some questions, maybe it would.
No, I think you've covered it pretty good. There is just one question because it's related. I had somebody once ask me, "Does negative energy exist in positive space, or does it exist in negative space?"
Negative space only.
Yes, that's why
Even
it's
with
negative.
Even with the Casimir, because in the Casimir plates, the plates are so close, they're blocking so much energy that leaves a negative in comparison.
That's
which
right.
means space is actually a little bit of a negative space-time poking through and mixing with positive space-time between the Casimir plates.
And that's the biggest thing.
If you emit light within that environment, that is one kind of more complex, higher-order electromagnetic radiation. See,
Yes.
It's actually already in front of us.
It's always been there before us.
Kind of like, I like to say it's like electric motors. If you went back to Roman times, you could teach them how to build an electric motor. They might not, and batteries and generators, they might not understand how it's supposed to be working, but you could teach them to build it. And we know that they had all the equipment you would need to.
Well, we also,
and yet, it took until the late 1800s for anyone to figure it out.
Yeah. Well, of course, there's the Baghdad batteries.
Yeah, which I speculate might have been used for electroplating.
Yeah. So...
And
of
the
course,
Greeks understood it well enough to build lightning rods of some of their temples.
Yeah. And of course, it wasn't reused until the 1800s.
1700s.
Yes, that's right. Absolutely.
With Benjamin Franklin and another
Franklin.
Another scientist, I think, in France, both independently, came up with the notion of a lightning rod.
Saving
if you think about it,
buildings, yes.
An electric motor is simple in principle.
Yes.
You have, let's see, what's the simplest example, I think, is where you've one wire with current going one way, another on the other side with current going the other, and then you have a magnet in between on a little freely spinning wheel, like armature.
Mm-hmm.
And then you just pulse the two. No, that's right. You have a little loop of wire on one side producing a magnetic field going one way, and then you have another one on the other side, and you just basically alternate them and pull the magnet back and forth between them.
Yes, that's right. You can have a rotating field that's...
Well, I'm just saying pulsing right now to simplify it.
Yeah.
The point is that kind of thing is really simple. They had lodestones or magnetite is what has been known about for thousands of years, and copper wire is something they would have made routinely for jewelry and whatnot.
Right.
Going all the way back to a little bit before the Bronze Age.
Even gold wires.
Yeah, so they could have easily made a motor and by inverse a generator. And a battery is not a complicated thing. It's...
Yes. Well, everyone knows the zinc-coated steel nail in a lemon or a potato produces...
So the point is that it's something that in hindsight is really, really obvious and really simple, but was just overlooked for literally thousands of years.
And so the analysis...
Likewise, these higher-order EM fields have been hiding in front of our noses for thousands of years. I mean, every time you have a magnetic field cancel itself, two magnetic fields opposing, there's this other higher-order field there undetected, because it's a little less interactive normal EM.
I wanted to make mention to there's a gentleman, and I'm sorry I don't remember his channel. He actually showed where by canceling magnetic fields, he could transmit a radio broadcast through a Faraday cage.
Yeah, because what happens is it's kind of a it's a trade-off. You're canceling out and reducing the wave or field's normal electromagnetic interaction and amplifying its other interactions. And so therefore it also means that Faraday cages don't stop it.
Yes, that's right.
In fact, this actually provides an answer to something that scientists have been hunting for, and that's dark light. Dark light. Because you could also call it a true black light, because it's light that is black, it's invisible.
Not to be confused with black light of the light bulb.
That's just a UV bulb.
Yeah.
But that, to a UV camera, is not black.
Right.
Whereas this would be truly black to all frequencies, unless you had a special receiver designed to interact with this radiation.
Yeah, then you'd be able to see it, yeah.
Scientists have been hunting for this because dark matter kind of needs another interaction other than gravity to fully explain its interactions.
Right.
But that is a completely different topic that we'll one day come back to.
Yes.
Back to jump drives, huh?
Yeah, let's, because I see that we're just over the 1 hour mark thereabout.
Okay, do you want to say some
approaching.
more, or should I continue?
Well, I wanted to make sure, and you please continue, let them, our first video we talked about York time, what White talked about, the bubble, the space-time contraction, expansion. I think we need to clear the air there. The contraction of space-time before the bubble.
Okay, then that's perfect, because the next part of my notes here is about that.
Okay.
So, as the speed of light, as a ship. Wow, my notes say as the ship of light is approached. Yeah.
Oh well. Yeah.
As the ship approaches, as a ship approaches the speed of light, to an observer back here on Terra, the ship appears to struggle to accelerate against what appears to be an decelerating force. So its acceleration, if it has the same thrust, its deceleration just drops and drops and drops.
An opposing force.
Yeah, as it approaches the speed of light.
Yes.
Now, the ship itself doesn't see that, but if it has a warp field, that is a field that counteracts time dilation, then the ship itself perceives this resistance as well. What happens is that as it travels through space, because you're trying to force space back into the way it looked when you were stationary, or back on Earth, back on Terra, and you're also trying to limit. You're basically trying to make your clock tick in sync with back home, and as a result, well, space doesn't like you trying to do that while you're plowing through it. It means that you can actually perceive your own relative motion. Space-time is streaming, so to speak, streaming past you and piling up in front of the ship, and it acts just like a ball moving through the air, an object moving through the air.
Yeah, where the air compresses in front.
Compresses in front, and then as it compresses it.
Sorry, go ahead.
Do you want to say it?
I was going to say the air compresses in the direction of the movement of the ball, and the space-time is doing the same thing. So go ahead.
It behaves like a supersonic airflow where the front of a vehicle, it sounds strange saying this, but acts like a convergence, because the air is free to go wherever it wants, and then suddenly there's a thing in the way, which means its degrees of freedom, its directions, ability to move in whatever direction it wants is restricted. Because there's a thing moving through it now, in the way, a solid surface that can't penetrate.
The space-time doesn't want to move out of the way.
I'm talking about air right now.
Yeah, okay, air, yes.
So the air, its number of degrees of freedom is reduced. With supersonic airflow, because the air doesn't want to move, if it can avoid it, doesn't want to move fast at the speed of sound, and yet its degrees of freedoms are reduced, its only option is to just compress and pile up and become denser and higher pressure. That forms a shockwave off the front of the vehicle. But then as it reaches the widest part of the vehicle, now the vehicle is from then on pinching away and diverging. So suddenly the air has more degrees of freedom than it did. So it expands out and accelerates because suddenly what happens when you have high pressure gas and you suddenly release it? It expands. Right?
Yep.
Pop a balloon, it expands. The balloon shoots off. That's what happens as it passes the widest part of the vehicle. It expands and acts like a rocket nozzle and accelerates. But then it accelerates so much that as the vehicle comes back to a pinch, suddenly the air is running into itself and converging again, and once again piles back up, forming a secondary shockwave. But generally speaking, looking at the first two, ignoring the pinching back together, let's just say that happens far behind. It piles up in front and then overexpands and overaccelerates in the back. Well, what happens as this warp bubble tries to push through space-time is the same thing. Space is complaining as you're trying to warp it flat, as it's trying to curve, and it's piling up and creating a very severe curvature in front, like a gravity field. Meanwhile, as it pushes past and around the bubble, it then expands rapidly and overexpands and forms a no, I want to say this. It's not technically contracting, expanding. Space cannot be contracted or expanded.
Right.
It just looks like that way because we cannot directly perceive time, the fourth dimension. We see 3 dimensions that are just constantly changing because we're stuck in a 3D view. And as a result, what's happening is that the space is actually curving in different directions into time.
We're creating a gravity well like that of a planet.
Like, in other words, if you try to contract space, if you try to force it to contract, it won't. Instead, it will contract in the positive time direction, and that creates a gravity well. Basically, gravity creates time. Which
creates a curvature. Space-time cannot compress, but it can curve.
That's what we call a positive curvature, because it's in the positive time direction.
Hence gravity.
But then if you try to expand spacing, you try and yank and rip it apart and pull it up larger, instead, it still will refuse to do that, and instead will expand into time the other direction, in forming a negative curvature, where time is into the negative time direction, slowing time down. Speeding time up, actually.
Speeding time up, right. That's the York time that White talks about.
And as White pointed out, it actually is unwanted because it takes energy to bend space-time.
Yeah.
So just like in the air, one way to avoid the shock wave is to use magnetohydrodynamic force fields to reach out, ionize the air, and reach out with these fields and grab hold of it. In the front, if you accelerate it, its pressure drops because you're basically pulling the air out of the way before it can pile up. Then as it over-accelerates at the wide part of the vehicle, you decelerate it, causing it to pile back up again and form the same pressure, so that the air moves around the vehicle at different speeds but at constant pressure.
Yep.
No shockwave, and the energy that would have to be expended normally shoved through it, instead free and available, you accelerate. And in fact, the air, as it's doing this, squeezes you forward out of the way by action-reaction.
Yeah. Helps to propel it. Yeah.
No sonic boom. In fact, no even thermal build-up.
No resistance, that's right. Yeah.
You can do the same thing with space-time. By making the fuzzier field like White was talking about. In fact, you can go more than his fuzzy field. If you extend it in a cone in front and behind you, you're basically more gradually modifying space-time.
Way out at the very front of the cone is when you start to curve space-time ever slightly, like we talked about with the debris.
Yep, and if you can do that smoothly enough, then you can get it moving around you at FTL speeds. And then as it comes back behind you, you bunch it up and decelerate it. And as a result, space-time moves around you smoothly, and the energy you'd waste on it piling up is suddenly free.
Yes.
You whip. So that's how you can actually exceed the speed of light without going instantaneous. But it's dangerous because it's still, even with as smooth as you can make it, with such speed, to particles sitting there in space and you race through it, your warp field is creating a huge gravitomagnetic field, rippling space severely, like you're right next to 2 black holes colliding.
Yeah.
It'll be effective gravitational shockwave despite your best attempts, simply because of how fast you're going.
Well, you'll look like a moving black hole.
You actually look like a moving white hole.
Yeah. Oh, that
will superheat anything you run into immediately into extremely hot plasma, which you can deflect electromagnetically. Now that's plasma. But that poses limits, because at some point... At some point, you won't be able to deflect it enough. Not to mention, then, this builds up behind you as this horrible beam of radiation, which you don't get to experience most of the time because you're out racing it. You only experience a bit at the front, most of it's being left behind. But once you stop, suddenly you're irradiated in the back by this for a little while, and whatever's in front of you gets beamed. If you are traveling for too long at too high a speed, you'll destroy whatever your destination is, even a star.
Yeah.
So the drive has limits. You'd have to operate in a kind of pulse mode to keep dissipating the radiation. Not to mention, you'll have to expend a lot of energy just to deflect, and there's another problem. In the older papers, they thought that warp drive had to be really thin, because they thought that the necessary kinds of energy could only exist in very small spaces. But as your viewers are probably well aware of, more recently, you don't need necessarily a tiny space. Or if you do, it's a tiny particle, not a tiny volume.
Yeah.
So there's no reason for the warp field, for the wall, so to speak, the transition zone of the warp field to be thin. And because the problem when it's thin is it acts like a black hole's event horizon and it boils the quantum vacuum, creating all manner of exotic particles, some of which have enough total energy to distort space-time and create little bubbles that penetrate through your warp field or even little tunnels through it. It's like your warp bubble just starts becoming like Swiss cheese, just bubbling, and it destabilizes. The way around that is making a fuzzier field, a more gentle disturbance, and you have less exotic particles created.
So
but to anything you're running into, to space-time you're plowing through, you're moving, and therefore your Lorentz contracted, and so the bubble in the direction that you're moving becomes contracted.
Yeah. Yes.
And therefore thinner. The key point is only along the axis of motion.
Yeah.
So therefore you have to constantly extend your field in the forward and backward directions along the axis of travel more and more the faster you go to compensate. And at some point you'll have to extend it impractically far and you won't be able to go any faster.
When the just to let everybody, to give everybody a better idea of what you're referring to as the bubble being thin and thick, it's analogous to having a planet with a very deep gravity well. As you come close to it, as the closer you get to it, the suddenly more acceleration you have. So, which is more analogous to a black hole. But
Something like that.
Yeah, but the softer, the bigger the field is between with the flat region in the center and the outer region of space-time, the thicker that is what Renee is referring to, the better. And the more likely you are to be able to to maintain the bubble. But as Renee was saying, there are other problems. See, Alcubierre himself says that one of the problems with the warp bubble is that these particles would materialize and overwhelm the bubble and destabilize it. But
like I said, that's due to the thinness of it.
The thinness. But as White first introduced, and as we're adding to, that by projecting it much larger forward and behind,
well, White was talking about just making it fuzzier overall.
Yes.
But you can take it further and extend it forward and backward with different field emitter geometries to create a smoother field still.
Like a cone, or actually more like a football, a U.S. football, for our English listeners.
It makes no sense. Why is it called a football?
That's another
football. Soccer, in the U.S. That's football. You kick it with your foot. That's real football.
That's right. Well, they should call it a hand in football, because you kick it with your foot.
What's called football in the U.S. should be called a handball. In fact, wasn't there an older name of a game like that?
I don't know
I've read
about
that somewhere.
But they should call it foot and hand, or hand and foot, because you do kick it once.
Anyway.
Yeah, moving on. So
whatever.
So the warp drive, we just described the warp drive as Alcubierre and White discuss it. But the jump drive is something different.
Basically, the warp field at high speeds then would take on a geometry that looks like the cross-section of a disk.
Yes, a flying saucer.
Which actually means a disk is actually a pretty good shape. Both in the air, there's that Romanian Adifo, they call it. Yep. They designed it by taking the shape of a dolphin's back, the back half of a dolphin, minus its tail, of course, and then just mirroring that around all the way around in a radial symmetry.
Yeah, 360 degrees, yes.
And it turns out, due to the way the geometry works, it actually largely eliminates a shock wave. It kind of accelerates and decelerates air the same way magnetohydrodynamic fields would.
Yes.
And it's also good coil geometry because then coil is already in the shape of the field you need it to be.
Which the coil can be within
You can prove it. You can prove it further by making a kind of a compliant field. So in other words, it's actively scanning, and as you're moving, the field gives in some spots because if you can take something and give a little bit, you can slow it down more gently than release it.
Yeah. It's not
same thing as, by the way, I think the key
method.
to storing antimatter, but that's a whole other topic.
Yeah. Yeah, that's another topic.
We should do a video about antimatter, making it, storing it, using it.
Yeah, we should.
A podcast.
Yeah.
If you guys want to see a podcast about antimatter, yell at us in the comments. Sure you will anyway.
Just put antimatter with like 5 exclamation marks.
And all in capitals.
All in capitals, shouting at us. So, the jump drive.
Yeah.
It's different than the warp drive. So now, explain to them how that works.
I'll make a quick note.
What's that?
I'm making a quick note.
Yeah.
Okay, so what was your question again?
Okay, so everyone's going to want to know, how does the jump drive differ from the warp drive?
Okay. Well, other than its instantaneous travel property, I'm going to start by you could describe it quantum mechanically. That's what Musha did in that Musha jump drive, but with a time quantum, with space-time being quantized, you can explain it from a relativity point of view, from the standpoint of relativity.
Yes.
It works like this. You have a time quantum, and acts kind of like a tick in a program or a game. One game tick, one game cycle, one cycle of code.
Mm-hmm.
So just like a game, there's a finite number of cycles per second, and everything that happens must be computed within those cycles, within one cycle.
Mm-hmm.
In the game, if you accelerate enough, even if the game, let's say, has a maximum speed limit, won't let you go beyond a certain speed, but you could cheat your way past it briefly anyway. If you were in the game to accelerate, if you go up to right below the maximum speed and then accelerate as much as you can, if you accelerate enough, you, for one game tick, would rapidly, because you're accelerating so much, in the next game tick, the calculated position of your ship is suddenly really far away. And because you can't go with speed, you're immediately decelerating on the next game tick. So you have, as far as the game's concerned, you're not actually moving. It doesn't realize that you just basically teleported. Does it make sense?
No. Remember what we talked about before, where if this was your analogy. You said that if in the game, if two objects happen to collide at a point within that tick rate.
That's not a perfect analogy, though, because that's to do with speed and not acceleration.
Yes. Well, it kind of...
I don't want to give the analogy here because
okay.
It can lead to a misunderstanding.
All right.
Hence, I'm saying like this. The game, let's say its maximum speed, it lets you go like a certain, space game... won't let you go over 300 meters a second.
Or 400 now, I think. Anyway.
Mm-hmm.
Yeah.
So, if you were to go up to right below that speed and you had some cheaty engine that allowed you to accelerate some ridiculous amount, the game will, of course, try to create a back acceleration to get rid of your acceleration as quickly as possible because it doesn't want you to go over that speed.
Right.
But, if you were to accelerate enough, then what would happen is that by the very next game tick, it would take your acceleration. It would, depending on how the game code is written, take your acceleration, and based on that, it's like, based on the acceleration, your speed would be this, and therefore you add that to your velocity, your position, and you'll be way over, and you'll be over here. then says, wait a minute, that acceleration is way too high. It cancels it. And it says that speed's way too high. It cancels it. But you've already moved.
Yes.
So in other words, you're cheating it by basically accelerating faster than the game can counteract that, and you're teleporting. You're instantaneously moving in the game, skipping a huge distance because the game has only finite rate at which it can do calculations.
Which is analogous to the tick of time.
Yeah, it's an imperfect analogy, but it works.
So
there's
you're saying that the ship effectively just jumped a great distance.
Yep. So here's how it works in reality. You have the time quantum, the chronon, from the Greek word. What is it? It is one because it's two words that are very similar, but pronounced a little differently. Give me a second.
Yeah, if I navigate away from this, it'll freeze up, so I can't reference the notes.
Okay, those two words in Greek, one is chronos and one is chronos.
Mm-hmm.
That's chronos and chronos. Chronos is the titan of agriculture, I think. But chronos is the Greek word ancient Greek word for time, the personification of time.
Mm-hmm.
So we have from that the word chronon. It means a time particle, a quantum of time.
A unit of time, yes.
Just like phonos means light, and so phonon is a particle of light, a quantum of electromagnetism. So that means there's a minimum amount of time that can possibly exist. If something the way it works in the equations, if something takes less than 1 chronon to happen, then it's tachyonic. And there's an associated distance associated with the chronon called the chronon wavelength. If something acts over the distance smaller than that, it's a tachyon. It acts like the speed of light, but is instead a lower limit on size and time, versus the speed of light is an upper limit on speed. So, if you accelerate so much that within less than 1 chronon, the ship has already moved some distance greater than light could in that time.
Yes.
Then, okay, so what happens is you're now moving faster than light. You've accelerated, and because you're accelerating so quickly, you are accelerating to a speed greater than that of light in less than 1 chronon. And because things that happen that fast are only tachyons, there's no thing stopping you until more than 1 chronon has passed, and then suddenly you're existing longer than a chronon. You cannot stay a tachyon anymore because you are inherently positive matter, which cannot exist in negative space-time and cannot exist superluminal, so you rapidly decelerate within less than 1 chronon of time. It's like an anillionth of a second. And so you suddenly, bang, reappear, creating an enormous shockwave because you're decelerating so quick. You can also view it that you emit Okay, I'm sorry, I'm ahead of myself. So you accelerate so much that in less than 1 time quantum, before space-time can react, you are traveling faster than light. Then, as that 1 chronon, as you approach the total elapsed amount of time approaches that of 1 chronon, you start condensing. You being inherently positive matter cannot exist as a tachyon in negative space-time for longer than 1 chronon. And therefore, massive forces and shockwaves appear, and you decelerate rapidly and reappear. But because you were for very, very, very briefly going faster than light, you've traveled some enormous distance instantaneously. And it's instantaneous because even though the chronon has a non-zero value, it acts as though it has 0, kind of like how a tick in a game. If the game is very laggy and 1 tick takes a whole second to calculate, right?
Yep.
The game is unaware of that. As far as the game is concerned, however long a game tick really takes, to the game, they are adjacent. It has no time interval. That's how the chronon also works. You were going to say?
Yeah, I was just going to, because it's a good idea to give different ways of different perspectives, offer different perspectives. So, for everyone to understand this, others, because I'm sure there's plenty who understand exactly what you said. Time is everything that takes place within. If you picture a chronon as having, let's say that each chronon is a millimeter in width. It's not, but let's just say that it is. Everything that happens that you are aware of, driving to work, your apple decaying, whatever it is, everything is happening within that millimeter. But the way time works, and this is why it's important that it's quantized, which means time comes in states of packets of time. Discrete chunks of time. So if each chronon is 1 millimeter wide, everything you are aware of happens within that millimeter. But the movement of time shows that there are multiple of these chronons side by side, and we're moving through and past each one of these millimeters. Now, but also between these chronons, we'll just arbitrarily say, for explanation only, that there's a millimeter gap between the chronons. Everything that takes place within the chronon is you are aware of, and it is normal matter. But when you move through that chronon and you're outside of that chronon and heading toward the next chronon, in between the two chronons is negative space. That's where nothing is, no normal matter exists.
That's where everything and nothing exists.
Everything and nothing. Yes. Yeah. That was good. So you can, while you're in this 1 millimeter chronon, accelerate up to the speed of light, and then via all that we've been talking about, you can then jump from one chronon into the next one and do so, or jump multiple chronons and do so while you're in the negative space. You can bypass all those other chronons, so to speak, and effectively travel instantaneous. So it's not a perfect analogy, but maybe some of you will understand why the quantization of reality is true. This is how time ticks. This is how we can have positive and negative energy side by side. The two work together to create all that we see. If we did not have a chronon, then we would just have negative space, and there would be no stars, no planets, no kitty cats, no...
You can also think about it like this, to give yet another description.
Yes.
It's as if everything you know and everything that's happening is continuously pausing for an extremely short amount of time, like in a millionth of a second.
Pausing,
or less.
Yes.
Everything just goes pause. Then it resumes again. Then pause, resumes again. Pause, resumes again.
Yep.
It's like we're just existing in a series of snapshots.
Well, that's a great analogy. Yeah, go ahead. Yeah.
Yeah, actually, because it's not so much that you're moving, pause, moving, pause, moving. It's more like pause, move, pause, move. And it's a series of snapshots of still frames, all chained together.
Like an old projector.
But you can't perceive that pause, so to you, it's continuous. You shine a laser a long way through space or watch distant starlight, you're like, no, there's no distortions or bubbles. That's because anything with positive energy cannot perceive that, unless, of course, like we're just describing it, accelerates enough.
Right. Or has a certain field around it that enables you
but generally speaking, most of the time it's unperceivable. That's also the trick of the jump drive, is that if everything's paused like that, if you accelerate enough, what you're happening is you're accelerating so much that from one still shot, you're here, and by the time it unpauses, whoa, you're way over there.
Yeah.
There's no time for anything, because there was no time. You're in a no-time space for anything to stop you. But at the same time, you can't keep it up, so you're no longer going at faster than light as soon as the universe unpauses again. As soon as the next snapshot comes through, you're no longer moving faster than light, but you've also gone really far.
That's right.
That trick, by the way, as another tangent, sorry.
Yeah.
You could use that to create something like the replicator or on Star Trek or the duplicator on Paro Dan.
Right.
Kind of prefer the name duplicator because it's duplicating its.
Yeah.
What is the difference between duplication versus replication? And, I love these kinds of free-ranging conversations because that's how we talk. It's the most interesting conversations are ones that kind of meander.
The meander and open up doors into other avenues to think about. That's why think tanks are so beneficial towards progress. But your analogy, and immediately when you were talking about it that way, I was thinking of the old movie films, the projectors.
Mm-hmm.
Because you could look at each picture is time. Each frame in between each picture is negative space, no time.
Well, to give an analogy that
relative to us, no time.
More recent generations might understand a little better. It's just like the frames of a movie.
Yeah, that's what I was saying. Yes,
like a series of stills. Anyone who's dabbled around in Windows Movie Maker you can go frame, or in YouTube now you can use the comma and period key, which also have those little arrows on them. The angle bracket. Sorry.
Yes.
No, dare I use the wrong term?
Yes.
The coder in me is ashamed. You can use those two buttons to go one frame at a time.
Right.
It's a series of stills. That's all any movie is, and that's kind of how the universe works.
And you did mention something there. So all matter in the universe, whilst in the chronon, is matter. Between the chronons, the question is, what happens to matter? What's it do?
Well, it's tachyons that also, guess what? It produces
flips. Yeah.
It produces particle wave duality.
Yes.
Because and this is in the paper, by the way, we're working on, so I don't want to go into too much details.
No.
Well, we're working on a paper on it.
Yes.
But yeah, it basically you have an oscillation between a tachyonic wave-like object and a solid particle. Now, what I wanted to say right there, I think duplicate is a better term, because replicate means to make a replica, a copy.
Right.
Whereas duplicate means to make to have an identical thing.
Yes, duplicate it. Yes, okay.
So, but you can make such a duplicator in real life using, if you had a series of particle accelerators, it'd be a gigantic machine, even just to make a tiny thing. It would accelerate a bunch of particles so that they would accelerate so much that they would do a tiny little hyperspace jump and reappear inside the chamber. Now, of course, I'd be going really fast, but there's ways around that. Like, there's something called a toroidal light pulse, and those have funky properties, very strange, unusual properties, where they can carry something inside and accelerate. And then what happens is that you can design them so they will, at beyond a focal point, dissipate. And then what happens is that as they dissipate, anything they're carrying gets rapidly decelerated. So if you could design a system that could make a accelerating, which you can accelerate light under certain circumstances. If you had an accelerating toroidal light pulse carrying something, it could carry a particle, the whole mass accelerates, disappears, reappears inside the chamber, and the pulse is designed so that right after the jump it will fall apart, rapidly decelerating the particle. And you have whole massive circle bank of these accelerators, all firing at the same time, so a bunch of particles instantaneously just materialize inside.
Yes.
Think something, a tiny gold bead exists in there with a complicated nanostructure.
Right.
And you could even do it more by, because these are jumping, if you could adjust exactly when it appears, you could have a machine running for like an hour, doing like this being accelerate, like every second, or less than that.
Yeah.
But make it so that each successive pulse, like the earliest ones jump, like say a second into an hour into the future, and the latest ones don't jump in time at all. So they actually, even though they're running, accelerating for an hour, at the end of that hour, suddenly the whole object appears instantaneously.
Yeah.
But you could do more than that, because the other day we're talking about how you could use a warp field in a static sense to speed up time.
Yes.
So if you could create like a warp field around these tubes, you could accelerate time and have it so that that whole hour gets compressed to us into 1 second, and at the same time the particles are jumping. So what happens to us is it all looks instant, and the machine just synthesizes a macroscopic object instantly.
You mean like what they did in Yamato?
Yeah, like the time fault.
The cartoon series, the time fault.
Space Battleship, yeah. It was actually called a time fault.
Oh, time
fault line?
Fault, yes. Okay.
Vault works too, in my opinion, though.
Yeah,
but that one, it was like a 10-fold increase. So if a ship took 10 years to build, to the outside it was done and coming out in just a year.
Yes. Yeah.
And seriously speaking, creating it, we might actually in the future near future here, create like what Tesla's Gigafactory, but automate it, and where it has self-optimizing, and a little further ahead still, start putting warp fields around it. Like even if you had a 1% increase, running long enough, that could result in a drastically higher production rate.
So this technology, everybody, is going to open the door to what looks like magic.
No, it's not just good for moving through space. It's good for so many other things.
A whole lot of other things. That's right. And
so coming back to... Oh, sorry.
Yeah, okay. Well, I think maybe we should probably start to wind it down.
I do have some more to say about the jump drive.
Yeah, that's fine.
Okay, so... There's another way to imagine a jump drive, and this is where a warp drive becomes a jump drive. Normal warp drives, like we were talking about, using, say, maybe these higher order EM fields to warp space. And there's a paper showing how normal EM fields will actually couple and warp space even beyond the speed of light. There's a recent paper called the charge dust solution.
Yes.
That does mean one way to do it maybe is create giant current loops through plasma around the ship, so like, warp plasma for real.
Yeah.
Because they could potentially hold much higher currents than a solid material could. Which, that means this new ship, this new propulsion system, the plasma magnet that's been come up with, you might be able to make a warp drive out of it.
Yeah.
In the very near future, then.
That's a field drive, everybody. Field drive.
By the way, we're going to be making a video on the plasma magnet before too long.
Yep.
And we're working with someone who's familiar with it and in contact with its original design creator.
Yeah.
And depending on the feedback we get, we might talk about the
warp field.
The possibility of using it as a field drive.
Yeah.
As a warp drive. So, normal warp fields are created using positive energies that then give rise to negative energies. Which is great and all, but it means that to go fast and fast requires more and more energy.
Yeah.
But there's another way. If you could create tachyons, that is, create particles that are already tachyons, which means you'd have to give them energy. Because they slow down the more energy they have. So you'd have to emit energy, maybe create a warp field by a conventional means to capture them with an enormous distortion. You give them energy, they slow down to just above the speed of light, and soar around your ship, and then you release it. And they all go racing away, dumping their energy as they accelerate. You could have bias, you could do this potentially even from a standstill in the far distant future. Like maybe in a couple thousand years. We might be able to do this. And what could happen is you release tachyons, and whereas a normal warp bubble looks to everyone who isn't going FTL like a giant tachyon, within the bubble, your walls do not exactly look like tachyons. At least it's positive energy then giving rise to tachyonic. But it's not initially tachyonic. With a tachyonic one, even to you, aboard the ship, it would look like the walls made of tachyons. No, you couldn't interact with them, but you wouldn't need to. You'd have to, or rather you couldn't, so you'd have to set it up to do what you need to do before you even start. So what you do, you create this tachyonic field with a bias, and it shoots off, carrying you, as the tachyons move, they have a warp bubble, that they're moving in parallel, like together in the same direction, creating a warp field moving along with them. And of course, any space-time inside is at standstill route to the bubble, so the ship and everything inside the bubble gets carried along with the tachyons. They accelerate exponentially as they dump energy, going faster and faster beyond the speed of light. So your ship very quickly goes off right beyond the speed of light, practically instantaneously.
Like a photon. Well,
more than a photon, actually more like a tachyon.
It
goes, but the thing is, the tachyons have freedom to go in negative space-time, and they can leak away. You can use that to cause yourself to reappear some distance away. Because they don't experience time as we do, but you can kind of... It's an imperfect analogy, but you can understand it kind of like this. If you go in... it basically works kind of like the tachyons will leak away not over time, but over distance. It's like after X amount of distance, the tachyons will all have leaked away. It's not that you're actually traveling through space yet. Because you're going so fast, the tachyons will quickly accelerate toward infinite speed. Which means that you'll exist in between for no time, which means you, like we talked about in the beginning, you don't exist in between at all. But the tachyons will leak away, and once too many of them have left, you're now positive again, overall, and, well, positive can't exist beyond the speed of light, so massive shockwaves build up and decelerate you. And bang, you decelerate, now being carried by the tachyons some enormous distance away instantaneously. Hence, it's a tachyonic warp drive that behaves as a jump drive. That's the key.
Which means that you dematerialize because you're now in the negative space.
But positive matter.
But your positive matter that's being dematerialized into negative.
And it can't stay there. Or rather, positive matter cannot stay in negative space-time for longer than one time quantum.
Right.
And so therefore, you will practically instantly rematerialize. But if the tachyons have been pre-charged with enough energy by your extremely strong conventional warp field, when you gather the tachyons together by giving them energy, and then you grabbed onto them and then let them go. Or rather, you grab on, they will gain energy and then find the way to get away as quickly as possible. So you have to act really quick, grab them as many as you can really quickly. And it's kind of like you try to grab water. You're going to grab it for a moment, hold it, and it's going to all squish out between your arms or fingers.
That's right, yeah.
So you grab it and go, and hope that you grabbed enough.
Yeah.
And you will teleport some enormous distance away.
And
so
something that everyone needs to know is that the tachyons can bounce around the entirety of the universe faster than one tick of time, faster than that chronon.
Well, of course, yeah.
Yeah. Okay, so carry on, please.
So, and it means in the very distant future, thousands of years from now, we will be able to create a ship that could be sitting on the ground, go up into space, pulls its drive, bing, and in a blink of an eye, it's now instantaneously hovering over the atmosphere of a distant colony, thousands of light years away, even in galaxies away, several galaxies away.
Yeah.
Like billions of light years away in a distant galaxy, hovering over the atmosphere of another planet, and then comes down and lands. In thousands of years in the future, we'll be able to do that eventually.
It's doable, yeah.
Now, the problem with that is that how do you even get those tachyons? That's where the jump drive that we'll have to be contending with for the foreseeable future comes in.
Yeah.
That process we described, the accelerating, provides the tachyons. So what you do is you create the conventional warp field using those higher order radiation. But their effective mass energy appears to increase after being emitted, which they draw from the quantum vacuum, hence it behaves like a quantum ramjet. Told you it was all connected.
Yeah. Yeah. That's
so
right.
as you go faster and faster and faster, Ronning showed in his old 1981 paper, or 1980 paper, that if you could harness even just 10% of the quantum vacuum energy available at any given speed, you could go from orbital velocity to the speed of light in just 4 dang hours.
Yep.
As the energies grow exponentially. With these higher order radiation, if you can emit it within strong enough field strengths, you could do it. And can we do it? Here's the thing. In the future with fusion drives and antimatter catalyzed fusion drives,
Yep.
you could eventually get to the point where, like, say, by the 2050s, 2060s, maybe 2070s, have drives that are putting out something like, have a power rating of something like 10 terawatts. For comparison, all of the planet today uses about, it's either 4 or 10 terawatts. It's a huge difference, I know, I don't remember offhand.
Yeah.
World energy consumption.
But basically, the engine is going to be able to produce, and the ship is going to need to utilize as much energy as the planet, of the entirety of the planet. That's a heck of a lot of energy.
Yeah, so the instantaneous energy that might be used in any given moment would be something like... Oh, okay, yeah, basically entire energy. Now, the thing is...
Mm-hmm.
Okay, hold on. So the fusion drive would put, or antimatter catalyzed fusion drive, or black hole power drive, singulator power drive, and singulator converter.
Yep.
Could put out, say, the antimatter catalyzed fusion drive, like the engine they have on James Cameron's Avatar with the ISV Valkyrie, it's called. Or, no, sorry, ISV Venture Star.
Mm-hmm. Yeah.
An engine like that, it puts out something like 10 terawatts of power at any given moment. If you siphoned off just a mere 10% of that, that's still a terawatt. That's 1,000 gigawatts, 1,000 times the output of a nuclear power plant.
Yeah.
On average. With that much energy, you could pump that through coils if they're aligned to pinch and create a high-order EM field potentially with a field strength of something like 1,000,000 Tesla, like a neutron star. But remember, these are higher-order EM fields that couple to space-time more strongly. So the distortion to create would be enough that, there you go, you have a quantum ramjet by the 2070s.
And
which also will reduce the mass of the vehicle, even at a standstill, so much that the 30 Gs you're accelerating with, what happens is the whole ship appears to accelerate, because your mass being reduced, the whole ship would accelerate at something like 1,000 Gs from a standing start. Meanwhile, the crew inside only feel about 1 G of force. I did this some rough back napkin calculation.
Yeah.
And the ship would just practically disappear. Go shoot off. 1,000 Gs racing away.
It would appear as though it teleported, yes.
And then the camera would race after panning it and catch it. And just be to start, if you have a long focus, start to be streaking by the camera.
Yeah.
As you're panning it. And the ship would just barrel off. The whole thing would be glowing because of the field around it and the drive.
Yeah.
Just be a giant ball of light.
Mostly white and maybe a little goldish. Yeah.
I don't know. Anyway, so... And from there, as the ship's speed increases, more and more energy is available from the quantum vacuum. So that... it reaches, just like a few hours later, reaches the speed of light. And the energy, as it approaches speed of light and those shockwave tries to form, because of the field, like we talked about, you're smoothing it out, you have all that energy available, your energy potential goes exponential as you reach the speed of light. Your mass goes down to very near zero, but what happens if you take a ship, think about it, if you take a mass that's being pushed on some amount, and then suddenly you drop its mass down to very near zero, its effective acceleration will skyrocket, because energy has to be conserved. If you drop the mass, the acceleration must go up.
Yep.
If you have the same force on it. So the ship suddenly will accelerate a tremendous amount by dropping the mass so much. Enough that the whole ship and the space around it becomes a tachyon. There's your tachyon through warp field. Plus, this field you're emitting, you have to emit it in a warp drive manner. So that will concentrate where the tachyons get gathered and accumulated. You have a tachyonic warp drive. And will go bink, instantaneously travel like 100 light years. And then the ship will have to put on the brakes and decelerate rapidly.
Yeah.
Now, entering and exiting hyperspace in that manner will produce an enormous shock wave. Because of that shock wave, you're harnessing for energy just before you jump and recreate it just after you rematerialize. But it's not as bad as a normal warp drive because, one, it's omnidirectional.
It's a spherical.
Because it's not that you're coming out of an invisible doorway, like in that game Dungeons and Dragons, they have the dimension door. Sorry.
Oh,
yeah. Anything.
Yeah.
Any of you who played that or watched it know what I'm talking about.
Yeah.
It's not like a dimension door. It's not an invisible door you just step out of thin air.
Magic door.
What it is that you are going into another dimension, you'd appear to shrink away. The analogy is like flatland. You push a sphere down to flatland, it goes from nothing to suddenly it looks like a circle that expands out to some size. If you pull it out, it shrinks away in all directions. Same thing, you imagine expanding it to hyperspace, to full 3D space. As you jump, you would, if you will, it's like you're shrinking away to nothing. And when you reappear, you expand into it from nothing.
Yeah.
So the shockwave is omnidirectional. It doesn't have any directionality to it. It's just coming in all directions. Your speed might compress it a bit, so there's a slight Doppler beaming effect, but generally be just omnidirectional. And, I mean, mostly gravitational, because it's not like a warp drive where you're picking up energy as you go, and then it's being dumped as you stop.
Yeah.
It's just an immediate, so it's just like running the warp drive for a pulse. Which is one of the main advantages of the jump drive. Not only do you not exist anywhere between, so you can't, no risk of running into anything or colliding with anything, not a star, not a black hole, nothing.
Unlike a warp drive.
Where you could run into stuff.
Right.
You can't. Not with a jump drive, you don't run into anything. And two, whereas a warp drive has to maintain a very strong, high field strength continuously, hence why it showed for a 2-week, 10 times speed of light flight to Alpha Centauri, you need Voyager turned into energy.
Yeah.
Antimatter Voyager, like you need take half of Voyager and turn it into antimatter and collide it with the other half, and that's how much energy you need.
Yeah, and continuously too.
But the jump drive, it doesn't need that ton amount of energy because it only needs to maintain that field strength briefly. So you can take a relatively small amount of energy and just pulse it really quickly. This is why black holes will be key because the fact that you can go and take, using the Penrose process, let's see. So a particle could extract up to 30% of the mass of the black hole. Basically, using the Penrose process on a spinning black hole, you could extract an enormous amount of energy, or a sizable amount of energy, but you can do it especially really, really quickly.
With a black hole, yeah. It allows you to extract it.
And a recent paper showed that every single spinning black hole has a ring singularity inside with a window to hyperspace. So it's technically already emitting tachyons, but just not detecting it.
Yeah, right.
The paper didn't talk about the tachyon part, but if it's a window to hyperspace, I'm not sure what else would come out of it.
Yeah. So basically, it's a window to no time relative to us. To us.
Using that would be the key in order to generate that final pulse. That's enough to. You have to take not that much energy, it's a sizable amount, but not that much, and pulse it really briefly so that the power rating, amount of work done in a given amount of time, is extremely large. Just for a single instant, create that enormous field strength acquired. But unlike warp drive, it doesn't need to keep it up; just pulse it once.
Right.
Hence, you can, for example, like Musha showed with his equations, that if you turned half of Earth to energy, so if you took Earth, made half of it into energy, and annihilated it all, that amount of energy would hurl you 60 times the distance to Andromeda. So that's some 60 million light years.
That is.
Or what is it? How far is it to Andromeda? Million light years or 10 million? I think it's.
I'm pretty sure it's 10 million.
No, wait. Geez, such professionals, they have to look this stuff up.
There's a lot to store in our heads.
It's 2.5 million light years.
Okay, not 10 million, not 1 million. Okay, 2.5. Got it.
So 60 times the distance of Andromeda would be 150 billion light years. Now, if that seems like a lot, That's a lot of energy, yes, but it goes up exponentially. If you did half the distance, it would require not 30%, not half of Earth turned to energy, but something like just a tenth. It's enough that gets into the range of the amount of energy put out by singularities, artificial singularities. Which means that artificial singularities don't just emit enough energy, they emit it in the right kind. They can pulse and hurl the ship intergalactic distances.
Yes, and that... So everybody, what that means is that it brings this technology closer to reality, to being feasible, practical.
So it sounds like science fiction, but
believe it or not,
wait. By the end of the next century, we'll be traveling routinely intergalactic distances. It sounds like, what? No, you're full of it. Time will tell.
Time will tell. Just stay around long enough and you'll see. That's not that far away, actually.
Yeah, there's those aging treatments that are being worked on, and
500% life extension. Yeah,
which is five times. So that means rather than 80, it becomes 400 years.
For 350 to 450 years.
Mm-hmm. And so
get ready, everybody! It's happening.
And also, if you think it's expensive and only for the rich,
nope.
The longevity researcher Aubrey de Grey. Yeah. He talked about how, in his assessment, governments are going to have to develop and provide sooner or later longevity treatments, very low cost or even free, because more and more people are demanding in different countries free healthcare, and the lifespan, like expectancy, is already going up, and the world is becoming more developed. And as a result, the cost of healthcare for countries is going up and up and up. Yeah. Whereas, if you could develop a longevity treatment, however much that costs, you give it to them once, and maybe they have repeat follow-up treatments, that's going to cost over the person's lifetime. It will cost, because they won't be suffering as many diseases caused by the degradation of the body in old age, their healthcare costs will be overall lower, even with, say, once every 5 to 10 years, another longevity treatment. It will be less.
Yeah.
And the body, depending on the nature of longevity treatment, could be more resistant to diseases and whatnot. So don't be too surprised here if sometime in the next decade or two, governments start declaring aging a kind of disease in need of a vaccine, and go on and start making a kind of anti-aging vaccine. It sounds strange to put it that way, but
a genetic alteration. Yeah.
Yeah, a little minor genetic alteration. The alteration really is minor.
Back to the jump jive for a moment, because I just thought of something.
So, sorry, we're not going to recognize the planet by the year by the time period of 2200s.
Yeah.
I also think the Star Trek timeline is
on par.
It's going to prove accurate.
Isn't that funny? And
except that we won't be going around with short lifespans. We'll be Vulcan lifespans.
And most everyone will look 30. That's
me. The weird thing is
45 years
of age. A parent and a child 30 years difference in age. When one's 300 years old, the other's 330, they're both going to look 30, 40 years old.
10 years difference.
And it's going to mean that in the future, there's going to be a whole generation of people that look all the same. For a long time, everyone's going to look the same age. It's kind of strange.
How old is your dad? 350.
Only?
Only? Really? How old are you?
Only
I've just reached 150, but
That's in the future, rather than a generation being 25, 30 years.
That's right.
More like 70, 100 years might be the future generation time period. Don't have kids until you're 100 years old.
Yeah.
Because compared to 400, that's just 25.
So jump drive, because we're now at about the 2-hour mark. This is probably one of the most informational packed videos we've done yet. Podcast.
Sorry if I did too much talking, but
no.
It's kind of my field of expertise.
Yeah, no, that's fine. I think it's great.
I would love to do a public presentation like at one of these Starship meetings in the future about this.
Now,
hey, if any of you know about a presentation that's virtually accessible, then let us know.
Virtually accessible, that's right. Let us know.
Not really, traveling's still not really practical.
Okay, if we can think of all of this stuff and realize the universe, those who are more advanced than us are already using this technology. They already have their saucers and spheroidals and other shapes out there.
And cubes.
Cubes, yes.
Oh, sorry, one more interruption, then I'll let you continue.
Yeah.
This is going to sound strange, but a cubicle spacecraft is actually a sign of an advanced civilization. That sounds like, what? Think about it like this. If it's a slower than light ship, and it's a big cube-shaped ship, then that means the species has to be advanced enough to go into space in a big way and build big things in space, either using in-space materials or hauling up from the ground. Either way, it means that they're fairly far along already.
Yeah, if that's a good point, yeah.
If it's capable of high speed, travel near the speed of light, or even excess of it, that means they have to be advanced enough to have powerful enough shielding systems to deflect particles and radiation far ahead of the ship because it's blunt. It's a big flat surface.
Because
and if they can keep that safe.
Yeah.
So a cube is actually a sign of a more mature civilization, a more advanced civilization.
Or maybe they don't have that technology and they're dumb.
No, because like
no, yeah. I'm sure somebody's going to say that. No, if they're
we're already building cube-shaped spacecraft.
Right. Yeah, I saw the picture.
Cubesats. It's called Cubesats.
Very because literally, yes.
Sure, a sphere uses less material to enclose a volume, but sometimes your intent isn't to minimize material, but say just maximize the practicality of it. And a flat cubicle shape is very modular. Things fit together neatly. Spheres are the problem that you have to put things up against a curve. You have a flat, square piece of machinery that won't fit the curve.
How do you put your...
There's a waste in space.
Yeah, how do you put your desk up against a curved wall?
That's minor problem, but same thing on a larger scale with a spherical ship.
That's right.
So it might be somewhat... It might actually take less effort and be faster to build cubicle ships, go figure, than spherical ones. So I wouldn't be too surprised if cubes become the standard like freighter shape in the future.
Well, that really depends on the type of manufacturing that we're making use of.
But at any given time, no matter how advanced manufacturing, it's a lot simpler to make a flat panel than it is a curved one.
Yes, it is.
Let alone for a sphere, one curved in two different directions.
Yeah, a compound curve.
Yeah, but ship shapes are a video for another... That's a topic for another video. You continue with what you were saying.
Yes. So if there are... We can think of it, which we have, and there are others that are more advanced who are not just thinking about it, they're making use of this technology. But we know that every time there's a jump, there's a signature that's given off. We will eventually be able to develop the technology to detect jumps.
Not just eventually. Here.
Yeah. No, I know, but let me say it.
Can
second.
Well,
and then you can.
Okay. Because I want to give a specific example so that if someone wants to, write a paper on this and try doing this, they can go ahead.
Yes, and I do want you to say that. So, but I just wanted to say, because this is exciting, sorry.
No, I don't apologize. I'm excited.
The day we have these detectors in hand, we're going to be shocked at the number of people jumping around our system.
Or at least in the space around nearby.
Yeah, in the nearby, not in the solar system, outside, because it'll be detectable for many, many light years.
Well, we should say we may be shocked. It depends on just how many intelligent species are on the galaxy. And galaxies may go through civilization cycles just like Earth does, just like a planet does.
Yeah, exactly.
If we're in the middle of a dark age, then I'm not going to see anything.
But what better to suddenly we go from we're completely alone then we have this detector that, there are a lot more signatures than I ever thought there would be. That would certainly make a big difference on the Earth, wouldn't it? Okay.
What kind of signature, then?
Gravitational.
Well, so if you think about the jump,
Yep.
there's going to be two main signatures.
Yep.
For one, it's going to be a gravitational shock wave, kind of like a black hole collision, but really fast.
Yes.
High frequency gravitational
Burst.
wave burst. And second, because it's suddenly slamming into space, it's going to throw the electrons in the interstellar medium aside violently and quickly, producing a really fast radio wave burst. Maybe even higher frequency than that.
Yeah.
But, so, well, you might our current gravitational wave telescopes are large. They're designed for low frequency. But there's another kind that not many have been built yet. It's simple though, it should be. But the focus has been on bigger ones for various reasons.
Yeah.
It's called the Weber bar.
The Weber bar.
Plus, I think the bigger ones are potentially more sensitive, a little more precise, but these Weber bars could still produce useful data. And how they work is that you basically just have a giant metal cylinder, it's really simple, that is tuned to resonate at a certain frequency, and then you have piezoelectric detectors on it. How it works is that when a gravitational wave at the resonant frequency or harmonic of it goes through the Weber bar, what happens is, normally a gravitational wave would move the whole thing. But if you have, say, a half wave frequency, like where the gravitational wave wavelength is half the resonant, half the width of this bar, of the cylinder, the bar as it's called.
Or some harmonic of it, yes.
Let's just say half.
Okay.
Then that means half of the bar will be contracted one way and the other half the other way. And you'll actually have a difference because the wave's small enough. The bar won't be just moved as a whole and nothing detected. It'll have a differential.
Yeah.
And the sensitivity is increased by having it tuned to resonate that frequency. So if the wave keeps up long enough, it'll go resonate, 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 resonate.
Right.
And piezoelectric sensors can then detect that resonating. Nowadays, we could probably actually detect the wobbling of it using a laser retroflector bouncing off the surface.
Yes, right.
And detect much smaller and finer.
Right.
In fact, you could do kind of like a normal gravitational detector where you have a very long laser. Maybe needs more thought. Like if you could bounce it off multiple bars and then combine them with interferometry, you could potentially amplify the signal and then run that through photo multiplier to amplify it further, and then read that final output signal.
Right.
And these bars can detect high-frequency gravitational waves because of their small size. If we built those, we might start seeing the signature of a jump drive would be really fast, really high frequency, and very powerful. And if we could get a read on any kind of parallax or anything, really close shock waves. Just if it's a frequent drive mechanism, then we'd see it just peppering the sky.
Yeah.
Especially in the galactic disk. Another signature would be maybe a little easier to detect is really short, like micro nanosecond or shorter radio wave pulses, as it disturbs the interstellar medium from its sudden arrival. It'd be like because you'd have the initial spike, and then as the ship is barreling at high speed and decelerating, there'd be a trail off as it's still disturbed, creating a shock wave.
Right.
And you might even detect beaming effects, because the pulse would be omnidirectional, but then the tail would be highly directional because that's from the ship going at high speed and decelerating.
Right.
So if you detected like a omnidirectional pulse, and then later in the year because the wave would travel for a long time, you then one detector detected a very directional pulse and another only the omnidirectional spike.
Yes.
That would be a signature of a jump drive. In fact, it makes you wonder if some of those fast radio bursts aren't jump drive signatures.
Yeah, they would need to be analyzed. Yeah.
We're probably missing the most sharp signatures, because those would be in the microwave frequency range, like several gigahertz higher frequency even. Yeah. And those don't get through the air so well. We would need a millimeter array or maybe a micrometer array in space in orbit of planet, just a giant, basically mesh with a millimeter gap between each part of the mesh.
Yeah.
And just in space, it'd be really simple, but we haven't built it.
And we could put even one out at the Lagrange point, opposite side of.
Or you could set it up on little posts on the far side of the moon so that it hides from Earth's radio noise.
Yeah, that too.
Of course, as we start to settle the solar system, radio noise will be increasingly hard to avoid.
Yes, it will.
They might start mandating putting radio telescopes. We might have to start putting radio telescopes far out into the, Pluto.
All of that we're talking about, I'm sure somebody's going to ask, can any of this technology be used for communication? Deep space, interstellar communication?
Well, a fast and light ship can be used to carry messages, like old-fashioned way, just like in pre-radio times, the message was carried, or pre-telegraph times, message had to be carried, and it was only as fast as the fastest transportation.
That's right.
But also, these waves, higher order waves, might be able to, if they're intense enough, distort space-time, that they're the very space-time they're traveling through, and go faster than light.
Right.
And form a kind of hyperwave. Plus, if you accelerate something and make it jump a short distance, even if it's just like 1 meter, that will produce chunk of radiation, some of which will be mixed with faster than light with tachyons, and you could get a tachyonic burst from every time that jumps. It would be kind of like it'd be really crude hyperwave communicator, or a sci-fi term is Ansible. It'd be a really crude Ansible, but
like a spark accelerator.
No, not handheld. It'd be the hyperwave equivalent of a spark gap radio wave. Radio.
Yeah.
Where a spark gap of the electrons jumping across the distance was used to create radio waves.
Or you meet
likewise
a crystal and a razor blade. Yeah.
No, that's more advanced.
Yes.
I'm talking about the really early first ones was just they took a spark gap and then used it to send telegraph type signals through the air as like a wireless telegraph.
That's right.
And the initial ones could be where you take a particle, you accelerate it so it jumps like say like a few centimeters instantaneously, and in the process produces a burst of tachyons.
Right.
Well, technically 2 bursts, but instantaneous is good enough.
Right.
And you'll get a hyperwave. You pulse that rapidly, you can communicate fast and light using these hyperwaves racing out. The detection range will be limited though, because even if you got them at a focused beam, they'd act like an X-wave, a perfect Bessel beam. No divergence. But they will leak away into superspace as they go. So the further away you are, the weaker the beam gets, even if it's not spreading.
But you could relay it between stations and amplify it.
So you could... Near term, we might use that in the very near future, like in the next 20 years, for, FTL communication across interplanetary distances. Yes. Which makes an interplanetary internet a little more practical.
Yeah. Yes, it does. Yeah. Mars and Earth all in one internet.
I don't know how fast, because it'd have to... It depends on the range. If it could go all the way from Earth to Mars, then it's instant. But if it can only, say, go a few hundred megameters, that's a few hundred thousand kilometers.
Yeah.
A few 100 million kilometers.
Yes.
Is it? No. 1 megameter is 1,000 kilometers. And so 100 megameters is 100,000. Okay, so it'd be a few 100,000 kilometers. That's as far as it can go. You need repeaters, and the repeaters would have to detect the signal, process it, repeat it. That would take time and add a delay, but still.
Oh, that would still be quicker than a laser beam.
Yeah. And so, like, you might say, it's quicker than a laser beam, and you might even compare the two. So part of the trip might be made by laser beam, part by hyperwave, and the total travel time might be, initially with their initial setup, maybe only about, it might actually be slower than light, like the average, but still it means that the lag would come down to enough that you could maybe go watch YouTube video on Mars live.
Yeah. Yeah.
Maybe, or at least you could receive your email not 4 to 45 minutes after it was sent, but a mere... I mean, that's pretty common anyway.
Well, it takes light 5.5 hours to reach Pluto. So, if we could cut that time down to Pluto,
but I mean, you're not gonna have too much of a demand for high-speed communication to Pluto.
Hey, wait a minute! Next week. Wait a minute. No.
I think that Jupiter and its orbit,
Uh-huh.
the Jovian system, will end up with a fairly sizable presence later on.
I think there might be
because of the resources there.
There might be several settlements around it.
And on its moons.
Yes.
Titan is very appealing for different reasons, and so might end up being depending on how useful it is, a major or minor settlement out at Saturn. But beyond that, Uranus, Neptune, and their moons aren't really interesting enough to warrant more than research outposts kind of manned like Antarctica.
Right.
Might not be too uncommon to have research outposts that spend a couple years at a time empty, and then a research team shows up and the equipment's just left there, so it's ready to go.
Yeah.
They get there, they warm it up, defrost the air, which is frozen. It's so cold, the air itself that was in there is frozen on every surface, and warm it all back up and get to work. Do what they need to, and then when they're done, they leave it and cool it, chill it down in a controlled manner, and leave it on stasis effectively.
Yes, that's right. And not to mention the crystals that they can use to absorb the oxygen.
But now we're getting off topic, and we should probably save this for another video. But
yes, it's over 2 hours now. So, okay, I'm ready to go.
See you guys next time.
Yes, as usual, keep wondering about space. Thank you.
Bye.